having had your nutritious food. Let's start today's class. Again, not very highly informative, but yet again you have to know all these things. We are coming to what is known as series resistors or combination of resistors and how voltage is being divided among them. Okay. Share. Okay. This was regarding superconductivity. So what all things did we discuss till now in basic electrical engineering? One was we were looked into what is electric charge, current, voltage, power, energy, all those things. Second were the circuit elements like the voltage source, current source, etc., where we discussed about dependent and independent current source, independent and independent voltage source, etc. And we also discussed about Ohm's law, in which we came across resistor, where the scientist called Ohm took the constant of proportionality as resistor. So resistance, the characteristic, the property resistance was now being represented by an element called resistor. Then we also discussed about Kirchhoff's laws. Kirchhoff's laws, both KCL and KVL. This is where we stand as of now. Now, today what we will discuss is the combination of resistors, how they can be combined, as you all know, in series as well as in parallel. Then why do we require some kind of a manipulation to make it single? If you have a number of resistors connected in series or connected in parallel, you are now trying to make them into a single resistor with the connected to a voltage source or current source. Why do we require that? Because, see, for example, if Rixin Dolma is coming to Trivandrum, CET, after a long time, and she wants to pack so many things, put so many things into her bag, and some restriction is there in the conveyance that she can take only one bag. So what she will do is, if she has to bring in so many of the vessels, one by one, or so many boxes, etc., she'll put one box inside another box inside another box, and so on, and rearrange all the things. Her dress also, she'll do some kind of change in which she is folding the dresses on all those things, and then keep everything in the same bag. So what has now happened is that so many things which would have otherwise been accommodated in other boxes, all those things that she wanted to take, she could accommodate within the same bag, or no information is lost. Nothing is gone. Everything has been gathered and put into the same box. So now it has become easy for her to travel. Only one bag, but she can travel very easily. So similarly, if you have combinations of resistors in so many ways, and being electrical engineers, you will have to become design engineers. So you will have to analyze what all voltages will be coming across some resistors, or maybe you will have to anticipate how much voltage should be given to so many of the loads. So you will have to know the effective resistance or equivalent resistance of a big network. So that is what we are going to try today. So first we'll think about the series combination. Series resistors and the voltage division. I'm just making you recollect whatever you have learned. Suppose I'll be going a little bit faster so that we can do more problems at the end. Okay. So I'll have this is plus minus V, R1, R2, R1, R2. Okay, I have terminals A, terminals B. This is plus minus V1 across R1, plus minus V2 across R2, and I have a current I flowing. So if this is the case, by Ohm's law, you know that V1 is equal to IR1, V2 is equal to IR2, same current flows. And by KVL, by applying KVL, you know that, and I'm considering a clockwise direction, okay. And when if I consider clockwise direction, you know, here it is minus V plus V1 plus V2 equal to 0. So that is V is equal to V1 plus V2, or if I substitute here IR1 plus IR2, or this I'll get as I into R1 plus R2, or I is equal to V by R1 plus R2, which I take as V by R equivalent. Or in a series circuit, now I know this can be, this is equal to this. So now this can be drawn as an equivalent of plus minus V and R equivalent. The same current I will flow. So that is how you say that in a series circuit, R equivalent is equal to R1 plus R2. I needn't pause here, I hope, because all of you know what it is. And then I can write R equivalent is equal to R1 plus R2 plus etc. up to Rn, which is equal to sigma n is equal to 1 to n Rn, where you have a number of resistors, not only R1 plus R2, up to Rn. And now, which means any series network or series combination of resistors can be replaced by a single resistor R equivalent. And to determine the voltage, this is important. Remember, voltage division, voltage across each resistance. Each resistor. That is, we had two resistors, isn't it? R1 and R2. One was V1. Voltage across one was V1. The voltage across other was V2. Now, if I determine the voltage across each of these resistors, V1, as you know, was IR1. I was nothing but V by R equivalent, R1 plus R2 into R1. Or which I can write this as R1 by, that is V1 is equal to R1 by R1 plus R2 into V. Similarly, I can also write V2 is equal to R2 by R1 plus R2 into V. Or one main thing that you have to remember is when two resistors are connected in series, or when resistors are connected in series, the voltage division is proportional to the resistance, the value of the resistance. So V1, the voltage which is across, or which is dropped, the voltage drop across R1 is proportional to R1. And voltage drop across R2, that is V2, is proportional to R2. Remember this. So when two resistors are in series, now what you have to notice that the source voltage V is divided among the resistors in direct proportion to their resistances. That is one important point that you have to note. So this kind of, or this is being used, or this is a principle of voltage divider. In some cases, you may require to have some voltage to be applied to some network, and they add another voltage to be applied to another network, but you have only one source, then you use something known as a voltage divider. This is the property that is being used in a voltage divider. So in general, I can write Vn is equal to Rn by R1 plus R2 plus etc. up to Rn, this much, into the source voltage. The source voltage is divided in this manner to get this voltage. I hope this much is clear. Now, I'm passing on to, I'm not even asking whether you have understood, because I am sure all these things you have learned. Second is parallel resistors, or resistors connected in parallel, and the other thing will come. It was voltage division in the previous case. This will be current division. Current division. Okay. So let me draw a circuit. I'll have be two resistors in parallel. Okay. I, R1, R2. Let this current be I1. Let this current be I2. Okay. Now you have to note one thing. This is a common node. There is no element in between. So let me name that node as, A. All these portion is similar to one point. No other, there is no element like this. So no element is there. This is equivalent to a node, say B. Okay. Always remember, whenever there is no elements in between, it is as good as a single node. Okay. Now, again, by Ohm's law, we know that V is equal to I1R I1R1 is equal to I2R2. Why do I write that? Because this voltage is being applied across R1. The same voltage does appear across R2 also. There is no division of voltage. Voltage remains the same because node A, node B. That is why I have mentioned node A and node B. Because this resistor R1 is connected. All of these things you know, but to make sure that you remember it once again. This resistor R1 is connected across node A and node B. This resistance R2 is also connected across node A and node B. So you can have only one voltage applied, the same voltage applied between R1 and R2. So that is why I said the source voltage V is equal to I1 R1. That is the same as I2 R2, or I1 is equal to V by R1. I2 is equal to V by R2. Now, by applying KCL, I know I is equal to I1 plus I2 because I am trying to check at node A. So let me apply KCL at node A. I have one current I coming into the node, I1 going out, I2 is going out of the node. So substituting that, I will get I is equal to, instead of I1, I will put V by R1. Instead of I2, I will put V by R2. V by R1 plus V by R2. That is equal to V into 1 by R1 plus 1 by R2, or V by R equivalent or R effective. So in a parallel circuit, now you know that 1 by R effective is equal to 1 by R1 plus 1 by R2 if you have only two resistors, or you normally write it as R equivalent is equal to R1 R2 by R1 plus R2. This is the equation that you have to remember when you come across parallel resistors and then combine them to make a single resistor like this. So now you have a single resistance and a single same current I flows, but I have R effective here. Okay, or R effective, or I remember writing it as R equivalent. Okay. And if you have a number of resistors, you will write it as 1 by R equivalent is equal to 1 by R1 plus 1 by R2, etc. up to 1 by plus 1 by Rn. That is all. Now, one main thing that you have to remember is note. R effective will be less than, always less than the smallest resistor in the parallel combination. Resistor in the parallel combination. Why is it that it is important? There are cases where you may require the same current to flow, same current I to flow, but you want there are cases where you will come across in your higher semesters where you want to reduce the already available resistance is there. You want to reduce the resistance so that from the same voltage source you may have to draw more current or whatever, change the current in there. So you may have to, there is already some amount of resistance in the device which you don't have the freedom of changing. So how will you change that? How will you change the resistance? One way is to add one more resistor in parallel, small resistor in parallel, so that the effective resistance goes down by a lot. So this is a very important point to note, because there are cases where you will have to reduce the already existing resistance. You may not have you could have done a series, you could have brought in a series resistance, etc. Some arrangement you could have changed that the whole resistance and brought in some series resistance which is lesser than the previous value. But then, for example, there are cases where, suppose I had a 5 ohm resistance there in the device. Okay, this is a device. So I want to, for some reason, I want to reduce this resistance. What I can do is, I can replace this resistance with a 2 ohm resistor. Okay. Okay. But then I may not be able to do that because I don't have the freedom to interfere with the already existing resistance or already existing network in that. So what I can do is, I can add something externally to it, a parallel resistance to it. Maybe some 1 ohm or a 2 ohm or a 3 ohm, 5 ohm itself. So that finally what will be the resistance? The resistance reduces to 2.5 ohm. 1 by 5 plus 1 by 5. Okay. Or 5 by 2. If the two resistors are equal, if R1 is equal to R2, in parallel, the resistance will become equal to R by 2, R1 by 2, which is the same as R2 by 2. So if I can add 5 ohm resistance in parallel to it, which I can do externally, then the effective resistance can come down. There are situations when this knowledge will come in handy. So always remember, when you have two resistors in parallel, and if they are of the same magnitude, same value, then resistance gets halved. Okay. Now to the current division of current. Okay, current division. Suppose I have two parallel resistors connected like this. I have I1, I have I2, and say this, whatever. Okay, current current source or whatever. I know I1 is equal to, this is R1, R2. I1, this is left to you. You can find out. I1 is equal to R2 by R1 plus R2 into I. And I2 is equal to R1 by R1 plus R2 into I. By substituting the relevant equations, etc., you will get this. Now, what you have to notice, in this case, the current is divided as in the other way. That is, the total current I is shared by the resistance in the inverse proportion of their resistors. That is, I1 depends on R2, how much the other resistance is taking. I2 depends on R1. This is the important point that you have to note. How much resistance is being added in parallel to the already existing resistance will determine whatever current flows through the other resistance. Okay. And also here you can even think about how that can be done. Suppose I short circuit this. Suppose I short circuit this. I2 now becomes equal to I, and I1 will become equal to 0. Suppose I provide a short circuit here, that is R2 is made equal to 0. If R2 is equal to 0, then what happens is that whole of the current flows through R2. Okay, suppose I open circuit it. Suppose I open circuit it. Okay, suppose I open circuit this. That is, I just open it. What happens? R2 is equal to infinity, and so I2 will become equal to 0. I1 will become equal to I. Whole of the current flows through R1. So these two things are also there. When you short circuit, when you put a short across any resistor, whole of the current flows through the, as in the case of human characteristic. If you have a chocolate, you go for chocolate rather than eat some other thing. Like short circuit is like a chocolate for current. If it finds chocolate, you will eat chocolate only. I don't know if any of you don't like chocolate. I am a fan of chocolate. I am a fan of sweet things like chocolate and like kapal mithai, the grounded chicky. And if I see those, I go on eating it instead of eating any of the other nutritious things. So similarly, the short circuit is like chocolate for current. Okay, so that is all. So what we discussed till now is that if resistors are in series, R series, R equivalent is equal to R1 plus R2. And if two resistors are in parallel, then R equivalent is equal to R1 R2 by R1 plus R2. Or 1 by R equivalent is equal to 1 by R1 plus 1 by R2, etc. Now let's do one problem. You all should draw. Now everyone should now listen more carefully. It's very easy for you, but still carefully. Please draw this circuit diagram along with me, okay? Find R equivalent of the given circuit. Okay. Let's all do it together. Since this is the first problem, let's do it together. Step 1. Step 1. I have directly identified two resistors in panel, 6 ohm and 3 ohm. So 6 ohm parallel to 3 ohm. I can always use this symbol for parallel. So I'll get 6 into 3 by 6 plus 3, which I'll get as 2 ohm. Okay. Step 2. Now let me identify if there are any series resistors. 1 ohm is in series with 5 ohm. Hope that is clear. I hope this is also clear. These two are connected between these two, which means they are parallel. This is connected to this is connected to this, and this. So 1 ohm is in series with 5 ohm, or I will get that as 1 plus 5 is equal to 6 ohm. Okay. So the new circuit now becomes, my new circuit now becomes something like this. So I'll have 4 ohm, then I will have 6 ohm, then I'll have 2 ohm, and these two combinations 6 and 3 combines again to become 2 ohm, and I'll have 8 ohm. This is A, this is B. Now my circuit reduced by using these two, I get this circuit. Okay. Then I go to step 3. If you have any doubts in between, you can ask. Okay. In step 3, what I can do is you can combine these two resistors, 2 ohm in series with 2 ohm. So that series is in parallel with 6 ohm, isn't it? Same node. So 4 ohm in parallel with 6 ohm. Parallel with 6 ohm. Which means I will get that as 4 into 6 by 4 plus 6. Which will be 4 into 6 by 4 plus, which you will get as 2.4 ohm. Okay. So that now I can redraw this circuit as 4 ohm and then another 2.4 ohm and then a 8 ohm. Now this has become very easy. You just have to go to the final step. Final step. Resistance will be R equivalent will be 4 plus 2.4 plus 8. Or you'll get this as 12 plus what? 14.4 ohm. Hope this is clear. Anyone?
Yes, ma'am.
Yes, ma'am.
Yes. So, actually, you may be feeling little bored. Okay, time is. You may be feeling little bit odd and bored because you can just directly write the answer. I know, but this is how you get it. Because I am teaching you basic electrical engineering, I have to go through this. So now the time is over. I'll give you one problem which you have to do by yourself, and we'll do this as a homework. Okay. So this is, let me draw this. Okay, try this as a homework. 10 ohm, 1 ohm, 1 ohm. Then you have a 5 ohm. All of you should try by yourself. Okay. And if you go wrong, it's okay. It is okay to go wrong in your homework rather than in your examination, isn't it? So just try. And then you have another resistance like this. It doesn't connect here. That is why I have shown this jumping. It doesn't connect to the other resistance. Okay. So you have 3 ohm, 6 ohm, 12 ohm, 4 ohm. Okay. Find the R effective or the equivalent or R equivalent for this network. Okay. So try. This is easy for you, but try. Finally, the answer that you have to get is 11.2 is the answer that you have to get. I will be loading this in the classroom also, but don't just look and copy. Just try to, find the answer and then check. One way of doing it is, if you are not very sure with all these things, you can note this as this is A, this is B. This can be taken as a node C. This can be taken as node D. This can be taken as, say, what the same node, no? So this is also B, this is also B. Remember that. Okay, this is also B. So if you look into 3 ohm resistor, 3 ohm resistor is connected between C and B. 6 ohm resistor is also connected between C and B. So they are in parallel. Similar kind of arguments should be looked at. Okay. So that is all for today. So I don't know how much you are attending, because it's like talking to a wall rather. Huh? So in the next class, what we'll be doing is we'll be going on to the star delta transformation, etc. Unless you have any more clarifications required in this.